So radioactive decay is what we're going to talk about today. Welcome back to another video. The first question is, what does it mean to decay? So to decay is to fall apart, to break into pieces or parts or something like that. And so what we're talking about in radioactive decay is the decay of atoms into smaller, lighter weight atoms. And this is based on events and activity that occurs in the nucleus of those atoms. First, we need to talk about nuclear symbols. So the nuclear symbols are the elemental symbols with the mass number on top and the atomic number on bottom. And so the atomic number is the number of protons. This is the number that you should get off the periodic table. The mass number is specific to that isotope, which is the number of protons and the number of neutrons that goes with that. There's different types of radioactive decay. There are more than this, but the three main ones we care about are alpha production, which produces an alpha particle, which is a helium nucleus, beta production, which produces an electron, or gamma ray production, which is a side effect basically of one of the other types of radioactive decay, but it also produces a gamma ray, which is a photon with very high energy. So it's basically in the electromagnetic spectrum. The important parts are that you have you lose these things from the nucleus. So nuclear stability, decay occurs when something's not stable. So there is a band of stability, which is where all the dots are that show you the band of stability, which shows you elements and isotopes of elements that are stable and won't undergo decay. Anything outside of this line is unstable and will undergo some sort of decay. Everything wants to be in the band. Alpha radiation is alpha decay. It is limited to very, very large nuclei. So these are nuclei that are trying to lose protons and neutrons to become lighter weight, to become more stable. And so beta radiation happens when you have too many neutrons, and those neutrons will decay and become a proton and an electron, and they will reduce the number of neutrons they have. Gamma radiation tends to occur with any of these as a byproduct. So alpha particles, they are the helium nucleus with a 2+ charge, mass number of 4, atomic number of 2. There's no electrons there, it's just the helium nucleus. The beta particle is an electron. Very seldom does it use the beta symbol. It's mostly just the electron symbol. But it does go either way. Gamma ray has no mass and has no charge, no atomic number associated with it. The mass of the alpha particle is heavy relative to the others, beta particle is light compared to the others, and the gamma ray has no mass compared to the others. It changes the nucleus, so the alpha particle decreases the mass number by 4 and decreases the atomic number by 2. Beta particle is the one that always messes people up, because it converts a neutron into a proton, so it doesn't change the mass number. The mass is still the same, mass number is still the same, and it increases the atomic number by 1. Gamma radiation doesn't change the nucleus, but it usually occurs when something else is changing the nucleus. Penetration depth is low for an alpha particle, medium for a beta particle, and goes through almost anything. Very high penetration depth on the gamma ray. Protection for alpha particle is provided by paper. So if you're in a field of alpha particles, wear a really big paper bag, or clothes. Clothes would be good, or protective suits. Beta particle emission is protected by thin aluminum. So that tinfoil hat may protect you from a little bit of radiation to the brain, but the rest of you is going to get irradiated. Gamma ray radiation, you need lead. So lead pajamas are pretty much the only way to go for gamma ray, or like 3 feet of concrete. The danger from alpha particle emission is pretty low. It's really, your skin actually protects you for the most part from alpha particle radiation, so it's not something that really affects you unless you eat it. There were actually, during the Cold War era and during early radiation experiments, there were actually some assassinations that were confirmed by alpha particle emitters. Very weird. Beta particle emission is kind of medium. It can go through your skin. It can definitely burn you and cause some problems. Gamma ray does not turn you into the Hulk. It will, in fact, just melt you. It actually irradiates and destroys your DNA, and by destroying your DNA, it prevents all of your cells from replicating and repairing themselves, and so you just kind of start to melt with sores inside and out, and like your body just can't repair itself and everything just falls apart. It's horrific. So moving on from here, those are decay. When we're talking about nuclear events, we're also going to talk about fission and fusion. So fission is when a heavy nucleus splits into two smaller nuclei with smaller mass numbers. And so you have a neutron that comes in and hits a nucleus. Uranium-235 is the most common fissionable material. It then splits and divides and forms lighter things and kicks off more neutrons, which hit more nuclei, which split more nuclei. Uranium-238 isn't fissionable, so this can't happen with uranium-238. So if a neutron hits that, just nothing happens. Remember, these are isotopes of uranium. Still all uranium, but has different isotopes mixed in. Fusion is combining. So fission is breaking apart. Fusion is combining things. So here we have tritium and deuterium combining together to form helium, and they release a phenomenal amount of energy, combining two light nuclei to form heavier, more stable nucleus. So fission, examples are fission bombs, nuclear power plants. Fusion, there are actually a few fusion bombs, but for the most part, the number one place that fusion occurs is in the sun and in stars. This is where we think of it the most. So all of this is related to Einstein's E equals mc squared, or delta E equals delta mc squared. So nuclear changes occur, and when they occur, you get small but measurable losses of mass. This loss of mass is called the mass defect, and it's converted to energy according to Einstein's equation. So the idea is that every time fusion happens, you lose a tiny bit of mass. The mass number doesn't change, but the actual mass does change. When fission occurs, a tiny bit of mass is lost, and you lose that tiny bit of mass, and it gets converted into energy. And this is where the energy comes from in nuclear events. So this happens even though delta M is very, very small, because c squared, the speed of light, is so huge. It is still a large amount of energy that's produced in nuclear reactions. So energy release, when we're talking about power production, chemical or coal burning, it produces 3.3 times 10 to the 7th joules per kilogram of coal burned. Fission, you'll notice that that is 4 orders of magnitude greater, 7, 8, 9, 10, 11, 12, 5 orders of magnitude later, I can't count. And then fusion is 2 orders of magnitude higher than fission. So fission and fusion produce so much energy compared to chemical reactions. Most of our power plants are fission-based, because you'll notice that the temperature is 1,000 Kelvin. That's something we can attain and something we can deal with. Fusion is 100 million Kelvin. It's just insane temperatures that you achieve in stars, and so it's really hard to get a fusion reactor that's safe and stable on the Earth to continue working. So this is a model of a fission reactor. There's the heating elements, the control rods, the reactor core. There's a heat exchanger that goes through that. That heats up a fluid that then generates steam. The steam turns a turbine, and that turbine produces the electricity.